Security. So, we shall be continuing our discussions on power attacks. In particular, in today's talk we shall be trying to look into various metrics which are often useful for evaluating and giving a quantitative evaluation of side channel attacks. We shall be looking into CPA on real traces of AES 128, like in the last classes we discussed about doing power attacks on simulated power traces. So, we shall be looking into some of the examples on real trace attacks. We shall be defining signal to noise ratio or SNR of power traces, and we shall be using it as a guideline to compare DPA on iterative architectures compared with serial architectures and a special scheme which is called as shuffled schemes. So, to begin with, there are different metrics for side channel attacks, and metrics are very useful because they provide us a quantitative framework to compare between the success rate of two side channel attacks. It can also be useful for kind of understanding whether a countermeasure is strong enough to protect against a side channel attack. So, two of the most useful metrics are success rate of a side channel attack adversary, and the second one is called as guessing entropy of an adversary. So, we shall be trying to define these two metrics in today's class. So, to begin with, what is a success rate of an adversary? So, side channel attack, as we have seen, works by a divide and conquer strategy where the key space is divided into several equivalent classes. Okay, like what we normally try to do in this attack is we try to understand whether a key belongs to a specific class. Okay. So, this class could be, for example, a Hamming weight class or a Hamming distance class. So, we try to take a key, we for example have a big key space, and we try to map that key from which is a member of that key space into a partition or into an equivalence class. For example, we say we might say, depending upon Hamming weight, if we are using Hamming weight as a power model or a leakage model, then we take a key and we try to map that into a given Hamming class. Okay, so suppose you are using 8 bits, then the Hamming class could be 0, 1, 2, 3, 4, so on till 8. So, we know that depending upon the partition, for example, like if the Hamming class is like 1, right, then there could be if I am considering a byte in the state matrix, then there could be 8 possible values, like the key could be 1, 0, 0, 0, 0 and so on, or 0, 1, so on, and then again followed by zeros, and or it could be like this till like 0 follow like contiguous zeros followed by 1. Okay, so therefore, right, the attack normally does not distinguish between keys which belong to the same class or partition. We can formalize, so suppose I want to formalize this notion, of an adversary, then let us use this variable Ek, where k is the key space, and Ek essentially stands or denotes the cryptographic implementation. So, it is, for example, it is an AES algorithm which has been implemented. Now, the adversary assumes a leakage model, and let the leakage model be denoted as L. The leakage model provides some information about the key or some other desirable information. For example, it could be, as I said, the Hamming weight of the key. Now, the adversary is often modeled as an efficient algorithm. So, it is often modeled as an efficient polynomial time algorithm, which is denoted by AEKL, and it is bounded by its time complexity tau, memory complexity m, and q queries, which means like it requires a time, I mean the adversary, in order to essentially return an equivalent of the key or the equivalence partition for the key, it requires time which is proportional to tau or denoted by tau, and the memory complexity is bounded by m, and it can make q queries. So, it is important to keep in mind that the adversary needs to be an efficient algorithm. So, we are not considering against unbounded adversaries in this case, we are considering computationally bounded adversaries. So, if you take such an adversary and imagine that the leakage, so the adversary in this case, as we know, is a side channel adversary. So, it not only sees the input and the output of an algorithm, but it also tries to exploit the leakage of an encryption algorithm or encryption implementation rather, and what it does is that it maps a key which belongs to the big key space k to a set within which it cannot distinguish. So, if for example, it can say that it belongs to a Hamming class say 4, but within 4 there could be several possible keys whose Hamming weights are 4, and it may not be able to distinguish between them or among them. So, we define these partitions by a notation S, and the mapping from the space key or from the space k to the space S is denoted by a function. That function is called gamma. Okay. So, we say that okay, let me from this key space choose k and then apply this function gamma, and then I get a small s. So, small s is essentially nothing but the mapping. Okay. So, typically of course, right, as you can see that if I am considering say 128 bit space, there are 2 to the power of 128 possibilities. Okay. And if I map them into the Hamming classes, there are 129 possible Hamming classes. So, 0, 1, 2, so on till 128. So, typically as we can see that the number of partitions or the number of Hamming classes for example is much smaller compared to the total number of keys. Like in the keys we have got 2 to the power of 128, which is very large, which we are basically narrowing down to only 129 possibilities. Okay. So, therefore, the cardinality of S is typically much smaller than the cardinality of K, and that is why our attack will be successful in that case. And the objective of the attack is to determine the classes to which a target K belongs with non-negligible probability. That is our objective. So, as an analogy, as I said, you can consider the Hamming weight class which divides the key space into equivalence classes or partitions. So, Hamming weight or Hamming distance could be used as an analogy to understand this experiment. So, let us see what do we do in this experiment. So, what we do here is, suppose like if you are considering right here an adversary, then the adversary based upon the ciphertext, because the ciphertext is already there with the adversary because it is a black box information, and the adversary has an additional side channel leakage information. So, now together with this, the adversary comes up with a guess vector, say we denote it by G, which is nothing but the key classes which are sorted in terms of descending order of being likely a candidate. For example, like it may happen that the guessing vector, if I consider the analogy of Hamming weight class, will tell me that essentially the key belongs to a guessing vector which is denoted as say 1, 2, 3. That means like it could be either Hamming weight class 1 or it could be Hamming weight 2 or it could be Hamming weight 3. But the attacker is saying that probably 1 is most likely. Okay. So, that is exactly what is meant by this guessing vector. So, therefore, the guessing vector typically is again we define this as an order O adversary if the guessing vector will come up with O such candidate classes. So, it will come up with a vector G1, G2 so on till GO, and of course, you can understand that O will be lesser than the number of possible partitions. It will lesser than and if I am talking about a 128 bit state, then and if I am considering 128 as the maximum Hamming weight possible, then there are 129 Hamming classes, then O would be lesser than 129, okay, because 129 is essentially the all possible cases. So, now the adversary returns this guessing vector G, okay, and the attack is said to be successful if the key class, that means suppose like if I take the correct key K and if I map it to S, belongs to this guessing vector. Okay, if it belongs to this guessing vector, then the attack is successful, else the attack is a failure. Okay. So, exactly this is modeled by this algorithm which says that I take an input which is K, L and EK. EK stands again for the encryption implementation, L stands for leakage, K stands for the possible key space, and the output is 0 or 1, which means either the experiment is successful or the experiment is a failure. So, if you take any member of this key space, say denoted by small k, and if I map this K to S, that means S is my correct key class, okay, and the attack or the adversary who is bounded by like tau, M and Q, as I said that it is a polynomial timely bounded adversary which can make at maximum Q queries, can make a memory access which is bounded by M and can run, means its runtime is bounded by tau, okay. So, then it basically returns a guessing vector which is denoted as G, which is nothing but G1 to GO. So, now if S does not belong to G, that means if this key class does not belong to G, then it returns 0, which means that the attack is a failure, and if it belongs to G, then the attack is successful, so it returns 1. So, the success rate essentially can be defined as nothing but the probability that this experiment returns a 1. If it returns a 1, then it means like that S belongs to G, and therefore, right, the adversary, which is an O, as I defined is to an O order adversary, is successful. That means if it can give O possible members of its guessing vector, then it is guaranteed, or it has got, like I would rather say it has got a high probability that the correct key class will belong to this guessing vector. Okay, this probability has to be more in order, ideally it should be 1. Okay, so therefore, right, the correct key class belongs in the guessing vector if the attack is success. Okay, so now note that in this experiment, right, we always have a remaining workload which is defined by O. Okay. So, this may be sometimes an inflexible definition, because we are not really like kind of giving a metric or giving a quantification on the remaining workload. Okay. And here exactly the definition of guessing entropy comes into play. So, therefore, right, this is other definition that is of importance, which is called as the guessing entropy of an adversary. So, the above metric for an Oth order attack implies the success rate for an attack where the remaining load is O key classes, because it comes up with the result that the guessing vector belongs to O key classes. Okay, and the correct key can belong to any one of them, right. So, therefore, the attack has a maximum of O key classes to which the required key or required k can belong. While the above definition is fixed with respect to the remaining workload, because the remaining workload is O, is defined by O, we define guessing entropy to provide a more flexible definition if I want to measure how the remaining workload reduces or diminishes, okay, with evolution or with maybe like more number of observations. So, if you want to measure that, then we will slightly modify this experiment. So, what we will say is that suppose again your input is K, L and Ek, the output right now we will say it to be a key class which is defined as I, okay, or denoted as I. So, again what I do is I take the key which is the correct key, I map it by the gamma function to S, I again obtain this guessing vector which is G1 to GO, but now I do not just say whether the attack is successful or not, rather I try to return the position in this guessing vector, because if I can tell the position in this guessing vector, then it means that there are, for example, if it starts from G1 and if G2 is my correct key, G2 is where is equal to S, then that means, right, G1 and G2 are both possible, okay, and that means that the remaining workload is essentially proportional to this returned I, okay, and ideally I will want that S, which is my correct key candidate, should be the first member of the guessing vector, because in that case, right, I have really resolved it, there is no remaining uncertainty about the key, okay. So, therefore, right, the attack in this case the guessing entropy is nothing but the expected value of I, okay, and that is denoted by this notation which says that it is the expected value of the expectation of the like if I denote this I to be a random variable, like rather this I is an exact value, but if I denote capture this I by a random variable, then the expectation of that random variable is what essentially gives us the guessing entropy of this experiment. So, therefore, this gives me a formal definition of the adversary against a key class variable S, and the experiment returns the position of the candidate key class in the guessing entropy vector. So, this is an important distinction or difference between the first experiment and the second experiment. Although they are quite closely connected, there is an interesting like I would say complementary nature of both the definitions. Okay, in one case it essentially gives you that the remaining entropy is O, so it doesn't really bother about that. It just bothers about the fact that whether you can bring the correct key class within that O possible guesses. And in the second experiment, right, we basically try to give you the position of that key candidate in the guessing vector. Okay, so therefore, both of them can be useful in analyzing the side channel attacks. So here are some experimental results. So for example, you can see that these are again like CPA done on simulated power traces, as we have discussed beforehand, and it is with and without noise. Okay, so the blue, so if you can observe, right, there is a blue line, and the blue line shows like there are like several wrong keys, and you can see that the ranking of the key, so if it is not very clearly, let me just spell it out. So it is basically the ranking of the key, that means the position of the key in the guessing vector, okay, is basically plotted with the number of traces. So what you expect is that with the evolution, with more and more traces, the guessing entropy should get reduced to 0, because like it is at the beginning, okay. So it basically the correct key is at the top, okay. So therefore what we are plotting out is the ranking of the key, and the idea is that as the ranking becomes like from, suppose it is initially 10, then becomes 9, and then gradually it becomes 1, then that means it is at the beginning, right, and therefore the entropy is minimum in that case. So in this case, right, there are several wrong keys which has been plotted, the rankings of several wrong keys, and there is a small blue line which basically tells us the guessing entropy of the correct key. So if you can observe here, then with around something like more than 40 into 200 traces, you will find that the blue line shows that the correct key trace essentially, the ranking of the correct key goes to 0. That means it is identified, okay. Now the interesting thing is that if you add noise, if you add like more noise to it, then you will find that this will become sluggish, and therefore like what will happen is that it will take more number of traces to get down to 0, okay, and therefore essentially that implies that if you add more noise, then the attack becomes difficult, and the experiment or the attack takes more number of traces to reduce the guessing entropy to 0, okay, or to essentially bring the correct key to the top of the list or the guessing vector, okay, so that is the objective behind the experiment. So therefore now let us see that what will happen if I like replace these simulated power traces with real power traces, okay. So when attacking real power traces, of course, right, the effect of electrical and algorithmic noise will come into effect, which we are trying to kind of model with our Gaussian noise, but in real experiments there will be more phenomenon, and the architecture often has got a strong effect on the algorithmic noise, okay. So as we will see in our discussion, it is often determined, it often determines something which is called as a SNR, or the signal to noise ratio, which quantifies the quality of the power traces. This in turn affects the success rate and the guessing entropy of the attacks, okay. So this in turn has got a strong effect on the success rate as well as the guessing entropy of the attacks. So what is an SNR of a power trace, okay. So consider a cipher which is like AES, which has got R rounds, and let S be a random variable representing the key dependent intermediate variable of E. For example, it could be the target like S box input, for example, or the target S box output if you are doing the attack from the plain text, okay. So S is called the target, and it satisfies of when S is equal to, you can denote it as S is equal to Fk star X, okay. So Fk star X could be something like like that X is like is a random variable which is representing, say, a part of the known plain text or the cipher text. You have got the correct key which is K star, and therefore you apply them to get the value or estimate of Fk star X, okay. Now note that Fk star also depends upon the leakage function of the hardware device, okay. So and this is called as a deterministic portion of leakage. Why deterministic? Because you can fix it by fixing the values of X as well as K star. You can pretty much assume that this part of the leakage remains constant over several runs of the encryption, okay. So therefore but at the same time the total leakage will be something more. So therefore, right, there will be some portion which is proportional with this Fk star X, and that is denoted as this A Fk star X, where A is some real constant to indicate the proportionality. Now this is basically superimposed with a portion which is called as NT, okay. So NT is nothing but the like it's basically a Gaussian, and as we have discussed, right, that at every time instance there is an amount of electrical and algorithmic noise which is coming into place, okay, and that is essentially modeled as NT. So therefore you can simplify this and write it as AS plus NT, where Fk star X is nothing but S, okay. So here is like as I have said, that NT is some Gaussian distribution NT which belongs to, say, n 0 sigma t, okay. Of course you can say that it is not 0, but then if you say it is mu, then you can bring that component into Fk star X and you can make the noise component mean around 0, okay. So that is without loss of generality we can write that the NT belongs to the normal distribution n 0 comma sigma t. So therefore, right, there is a very important concept which is essentially when we talk about distinguishers, which is called as univariate and multivariate distinguishers. So, now let us understand what is meant by these two terms. So, in the above equation, AS, as I said, is a deterministic part of the leakage. It can be simulated by the adversary knowing the values of x and for each hypothesis of the keys. Like I make the, like I am basically guessing on a portion of the key. So, I may make a guess on the key, like there could be, for example, as we have seen 256 possible guesses of a part of the AES key when we are guessing, say, the 10th round byte, for example, and we can essentially simulate the simulate this portion. Okay. So, now the time instance when the target S is manipulated is called as the instance of interest. Note that, like if you are observing the power profile, okay, not every time instance is when that particular, like if you are targeting, for example, a specific state, that state comes into play. There could be other time instances when that state is not at all into the picture. Okay, it is not participating in the computation. So, therefore, right, there is a specific time instance which we call as the instance of interest, say I denote it as T star, when it is like this particular state is participating in the computation. Okay. Note that for most practical cases I do not know what is T star, right, we do not know what is the value of T star. So, therefore, in the most common form of DPA or in some of the forms of what is called as which is most practical, and as we have seen even in the context of CPA and difference of mean based DPA, an attacker applies a univariate distinguisher at each time instance. Okay. So, what is a univariate distinguisher? Univariate distinguisher is, as we have seen, the Pearson's correlation, for example, you are applying the distinguisher on a single point in the trace. You are applying it on a single leakage point in the trace. You are not applying it on multiple leakage points on the trace. Okay. So, if you apply it on a single leakage point on the trace, then you call that as a univariate distinguisher. So, what I do is, therefore, at all time instances, say T1, T2, T3 and so on, I apply this distinguisher. Okay. Note that if I have got a block cipher and the block cipher is basically like iterating over, say, R rounds, and in every R round there are T instances when you are basically sampling, okay, or T is a number of samples per round, then the total value of small t can range from 0 to RT, right, because it can basically go on from 0 to more precisely 0 to RT minus 1. Okay. So, therefore, if the observed leakage be denoted as Fkx, the attacker computes the distinguisher vector which is denoted as gt. So, what I do is, therefore, I evaluate this distinguisher at every point on the leakage trace. Okay. So, therefore, as you can see, this dt comprises of the result of this univariate distinguisher for all the possible key hypotheses. Okay. If there are 256 hypotheses, then you basically guess D1, D2, D3 till so on till D2 256. Okay. And how do you get any decay is as simple as that. You basically apply your univariate distinguisher on Fkx. So, Fkx is the actual leakage because k is the actual key which you do not know as an adversary, and this is the part which you are modeling. So, you are saying that, okay, I know, say I can simulate Fk star x plus there is a Gaussian noise that I am trying to model. Okay. So, therefore, right, if I basically take this component and if I say for example correlate with Fkx or if I apply any other distinguisher for that matter, I can apply any distinguishing function and then I get the value of dk. Okay. And therefore, the final result is based on the best among all these time instances. So, therefore, basically what I try to do is I try to kind of distinguish the correct key from the wrong key, right. So, if I know that I want to basically see that in which particular time instance the separation between the correct key and the second correct key is maximum, and that I try to kind of find out at all these time instances, and I want to basically tell that at which time instance this separation is maximum. Okay. And that would probably be returned as my correct key, correct time instance or T star. So, this is one approach. This is typically what is called as the univariate way of actually doing differential power attacks. Now, as opposed to this, right, in the multivariate approach, what you can do is that the attacker will use multivariate distinguisher which jointly evaluates the power consumptions at multiple time samples. Okay, so therefore, and this is very common in profile attacks. As we have seen, like the DPA that we have been studying is more an example of a non-profile attack. In a profile attack, this is probably more common, where you try to kind of apply this multivariate distinguisher on several points or multiple points on the traces. Okay. This can be, for example, very useful when suppose you are doing a computation not at one time instance, but it is spread across time instances. Okay. So, you are doing, say, in a sequential manner you are doing a computation. So, then what happens is that a computation is basically spread across different time instances in the power trace. Okay. So, in such scenarios, this is a more common form of doing attacks. Okay. However, like this is, we have to basically apply this in a careful manner. So, if you basically the objective of applying a multivariate distinguisher is actually to amplify your signal, or like to reduce the noise component. But at the same point, like this technique could be vulnerable to a decrease in success rate due to some points in the trace having less signal, which you are trying to combine with the high SNR points. Okay. So, why is it kind of more common in template attacks? Because in template attacks, when you are doing a profiling, at that point you know the key because you have full control on the device. Okay, and therefore you can estimate the SNR properly, and therefore you can suitably like combine those points. Whereas in a non-profile setting, you do not know the key, and therefore there is a chance that if you are arbitrarily applying this technique, then it may lead to like an overall degradation of the SNR. Okay. So, hence when high SNR points in the trace are combined with low SNR points, this could lead to a decrease in the overall success rate, and therefore we have to carefully apply this technique. Okay. So, this essentially brings us to something which is called as a definition of SNR, and that is a very vital definition. We will take up that in the next class. So, thank you for your attention.